Good morning, everybody. In the previous session, we had talked about Ybus by the method of inspection. We had covered few problems on Ybus by inspection as well. Next, we'll be proceeding with primitive network, representation of primitive network, a sample problem on primitive network, and then we'll move on to Ybus by the method of singular transformation. So first, let us see what is primitive network. For that, we have to understand what is primitive element. See, the definition says fundamental element that is not connected to any other element in the network. Such an element is called primitive element. Earlier in this module, we had studied about graph. When we were given with a circuit diagram, we had replaced all the passive elements as well as active element by lines to obtain the graph. So from the power system network also, the transmission lines were replaced by lines to obtain the graph. We had understood how to draw the oriented graph. Then we had written element node incidence matrix, bus incidence matrix from the same, and so on. So that element is nothing but one of the transmission line element. If there is any other element, if there is any element in the system which is not connected to other elements, such an element is called primitive element. Whenever you have a graph, generally the elements will be interconnected by different nodes. Say if you're having a 3-bus or 4-bus power system network, 4 buses will be there. All the 4 buses will be connected by transmission lines. So all the transmission lines there are interconnected. So whenever you are having any open element which is not connected to any other transmission line element, such an element is called primitive element. Set of such unconnected elements will give us primitive network. Set of primitive elements will give us primitive network. So whenever we deal with primitive network, we have two ways of representing them. One is impedance form, the other one is admittance form. So here we are able to see impedance form representation. So here you have EPQ, you have impedance ZPQ, and this element, primitive element, is called as PQ. On either sides you can see P and Q. This is element PQ. Element PQ has got source voltage EPQ followed by series impedance ZPQ. And let the current flowing through this element PQ be IPQ. Potential at the end P is said to be capital E subscript P. Potential at the end Q is supposed to be EQ. And then if you try to write the expression for potential difference across the element, VPQ will be equal to EP minus EQ, assuming that the current flows from higher potential to lower potential. We have taken the direction of current to flow from P to Q. Hence, we are assuming that P is at a higher potential compared to Q. So we write VPQ is equal to EP minus EQ. ZPQ is the impedance of this element. EPQ is the source voltage. Now, you can see the nomenclature. VPQ is voltage across element PQ. EPQ is source voltage in series with element PQ. IPQ is current through the element PQ. And we will come across JPQ in the admittance form representation. That will be source current in parallel with PQ. And self-impedance is ZPQ. Self-admittance will be YPQ. So this is impedance form representation of the primitive network. So here you have, primitive element. So here for this primitive element, you are representing it with a source in series with impedance. Then we can write performance equation for this impedance form representation. In order to get the performance equation, we just have to apply KVL here to write the performance equation. So from this expression, you can see VPQ plus EPQ should be equal to ZPQ into IPQ. So I into Z, it will be equal to VPQ plus EPQ. So this is nothing but performance equation for this given element in impedance form. So we'll call this as equation number 1. This is obtained by using KVL. Next, we have another form of representation which is called admittance form representation, where we apply source transformation for the given network element. For the primitive element that is represented here contains voltage source in series with impedance. If you apply source transformation, you get current source in parallel with admittance. So this particular current source which I'm showing here is nothing but JPQ, which is the current source. As usual, element PQ, EP and EQ potential at either ends, and then here instead of impedance it is admittance. So instead of having voltage in series with impedance, I'm having current source in series in parallel with admittance. Now the current that is entering this point is IPQ plus JPQ. JPQ is the source current, IPQ is the current through element PQ. If you add them, the current that is entering this part of the network is IPQ plus JPQ. And as usual, VPQ is EP minus EQ. Now for this admittance form representation also, we can modify the performance equation, which gives us IPQ plus JPQ is equal to YPQ into VPQ. I plus J is equal to Y into V in general, where JPQ will be equal to minus YPQ into EPQ, the other way of writing it. Now, this is called as equation number 2. Equation 1 and equation 2 are called as performance equations. So equation 1 is VPQ plus EPQ is equal to ZPQ into IPQ, which we have written using applying KVL for this given representation. And here we have done the source transformation and then written the other equation. Now, from this performance equation of the primitive network, we can derive the elements. We can derive the unknown elements here by expressing these variables as vectors and parameters as matrices. So we rewrite the equations 1 and 2 in this form. For in impedance form, when you rewrite, you can write it in vector form. Variables can be treated as vectors. So V plus E is equal to matrix Z into vector I. So we have VPQ plus EPQ is equal to ZPQ into IPQ, where V, E and I are treated as vectors, Z is treated as a matrix. So we have V plus E vector will be equal to Z matrix into I vector. Similarly, we do the same for second equation. We know that I, J and V are represented as vectors. Y is a matrix which relates these two. So I vector plus J vector is equal to Y matrix into V vector, where this Z and Y are called as primitive matrices. Z is primitive impedance matrix, Y is primitive admittance matrix. So it is represented as Y PRI, Z PRI. E, J are source vectors, V and I are element voltage and current vectors. So these are equations 3 and 4. So we have modified equations 1 and 2, treated variables as vectors, parameters as matrices, and these are the equations. Now here our intention is to find Z and Y. If we are able to find Z and Y, when these equations are solved, unknowns can be found. This ZPRI, what you can see, this particular matrix, we are talking about the nature of this matrix, how to write this matrix. Similarly, Y matrix. So ZPRI is basically a matrix having diagonal elements as well as off diagonal elements. Diagonal elements will generally be the self-impedance of the element. Off diagonal entries will be mutual impedances of the element. Whenever a particular element is mutually coupled with other element, the mutual impedance will be represented as off diagonal entries, while the self impedance will be represented as diagonal entries. This is true for Y primitive also. Here you have self impedance, here you have self admittance. Representation ZPQ comma PQ, YPQ comma PQ, which says they are diagonal entries, self impedances. If we want to write Y, if we want to get Y primitive, if you can take inverse of Z primitive matrix, you will be getting Y primitive. And here, whenever there is no mutual coupling present between the corresponding primitive elements, then both these matrices will be diagonal in nature. That means only diagonal elements with self-impedances will exist, off-diagonal elements will be zeros. If mutual coupling exists, off-diagonal elements will be present and they will be representing the mutual impedances. So this concept will be able to understand taking up a problem. So in this problem we can say, consider three passive elements whose data is given below. Obtain primitive impedance matrix and primitive admittance matrix. We have three such passive elements. We had seen element PQ. Like that, we have three elements here: element number 1, element number 2, element number 3, element, and this is ZK per unit. Second column is ZK per unit, which represents self impedance. J.6 for the first element, J.5 for the second element, and J.7 for the third element. All are complex numbers represented in per unit. Then with the third column is mutual impedance data, which is not existing for element number 1. For second element, it is J.2. In bracket, it is mentioned with element 1. That is, element 2 is mutually coupled with element number 1. And third element, there is no mutual coupling. So there is mutual coupling existing between element 2 and element 1. Now here we are supposed to obtain both primitive impedance matrix and primitive admittance matrix. So we have to write primitive impedance matrix, and if we take the inverse of the same, we'll be getting primitive admittance matrix. So whenever you're writing Z primitive matrix, the number of elements are 3. So the size of the matrix will be 3 cross 3. So here we are given with 3 passive elements with the data. When the elements are 3, size will be 3 cross 3. It will be a square matrix. Size is 3 cross 3. Then, as I told earlier, the self impedances will be the diagonal entries. Mutual impedance will be off diagonal entries. So you can see here, for element 1, self impedance is J.6, element 2, J.5, element 3, J.7. So Z11 will be J.6, Z22 will be J.5, Z33 will be J.7. Self-impedance with respect to element 1, self-impedance with respect to element 2, self-impedance with respect to element number 3. So your Z primitive 11, 22, 33 will be self-impedance data J.6, J.5, J.7. Next we have to write the off-diagonal elements. So here from the problem we can see that element 2 is coupled with element 1 with impedance J.2. So cell number Z12 and Z21 will exist because mutual coupling is present between element 1 and element 2. So your Z12 and Z21 will be J.2 where mutual coupling exists. So we have written the off diagonal entries, and in the remaining columns we write zeros because there won't be there is no mutual coupling present in those elements as per the given data. So this is our Z primitive matrix. I repeat once again, whenever we are writing Z primitive matrix, number of elements will define the size of the matrix first. In the problem we have 3 elements, so size is 3 cross 3. So the size is defined. Once the size is defined, first write down the diagonal elements of the matrix. For writing the diagonal elements, they are straight away the self impedances that are given for the element. Element 1, 2, 3, J.6, J.5, J.7. Write it as diagonal entries. Then check where the mutual coupling is existing. Mutual coupling is existing with respect to element 2 and element 1. So Z12 and Z21 will be this value J.2. So we have Z12, we have Z21 as J.2. Remaining elements are zeros. This is how we write Z primitive matrix. Then to get Y primitive, as usual, you have to take the inverse of a matrix. Y primitive is given by Z primitive inverse. So we have to calculate the inverse of this. Anyway, I have not shown the calculation. It is pretty easier, and it's already been covered in basic mathematics. So you should be able to get the inverse of this matrix. Finally, we get this value minus 1.92J, 0.7692J, 0, and J.7692, minus 2.3J, 0, 0, 0, and minus J1.42. So as usual, I think we should be familiar with adjoint of a matrix, cofactor of a matrix. All those calculations have to be done, and then inverse have to be found. Since it's a complex number, you cannot use your calculator for finding the inverse. You'll have to solve it manually and find the Y primitive matrix. So this is how we write primitive matrix. And examination point of view, this definition and derivation will be there in almost every paper. They'll ask you to explain the concept of primitive network and obtain the representation in impedance form and admittance form. This is what you are supposed to do. Define primitive element, define primitive network, represent it in impedance form, write down the performance equation 1, and represent the same in admittance form, write down the performance equations, and then go for alternative representations with the variables as vectors, parameters as matrices to get equation 3, 4, name all of this, and then just explain how to write Z primitive, how to write Y primitive. This is all. And in case a problem is asked, if of this variety, it will be asked. In case mutual impedance is not present, only diagonal entries will be there. So this finishes the primitive network and primitive element. Next, we'll move on to Ybus by the method of singular transformation. Earlier, we had seen Ybus by the method of inspection, where when we were given with an oriented graph, we used to write Ybus. Diagonal elements we used to write by adding all the admittances of the line connected to that particular bus or node, and off diagonal elements of Ybus we used to write by taking negative summation of the admittance directly connected between the respective lines. That is how we have written Ybus by inspection. Now, there were some drawbacks with Ybus by inspection. Whenever there is mutual coupling present, we cannot use inspection method. We have to go by singular transformation method. So the major drawback is presence of mutual coupling. In such a case, we cannot use method 1. We'll have to go for singular transformation. So here, let us consider a sample 3-bus power system network shown below. Bus 1, we have bus 2, and we have bus 0, which is the reference bus. And we have taken the direction of current flow and numbering for the transmission elements. This is element number 1. Current is said to flow from 1 to 2. This is rather than current, we can say power is flowing between 1 to 2, between bus 2 and 0, element number 2, and between bus 0 and bus 1, element number 3, with the corresponding direction. Bus 0, the third bus taken as reference, we have bus 1 and bus 2. Now, we are interested in writing bus incidence matrix for this. So if you have to write bus incidence matrix, first we have to go get the oriented graph. Already we have learned how to get the oriented graph for a given power system network. We just have to replace these buses by nodes and the elements, the passive elements that are connected here by lines. Passive elements, since passive elements are nothing but this is a transmission line. So transmission line will contain impedance. So we have not represented the impedance here. We are replacing those elements by lines. And then we are marking actively the bus numbers within the circle and element numbers within brackets along with the directions to get the oriented graph. So from this oriented graph, we'll have to write element node incidence matrix A cap. So elements vertically, nodes represented horizontally. There are 3 elements here, element 1, element 2, and element 3. So write it as element 1, 2, and 3. And coming to the nodes, 1, 2, and 0 are the nodes. So I'll be writing 1, 2, and 0 over here. Once this is done, let us write down the matrix elements. So coming to the matrix elements, first come to the element number 1. Element number 1 starts from 1 and goes towards 2. As discussed earlier, we just try to take the source node and the destination node. So source node will be written as positive, destination node will be written as negative as per the convention. So for element 1, it is from 1 to 2. So element number 1, that is the first row we start writing. It starts from node number 1, ends at node number 2. So under 1 we write +1, under 2 we write -1. 0 node is not involved here, write it as 0. Let us go to the second row. Second row we are talking about second element. So element 2 is starting at 2 going towards 0. So 2 will be positive, 0 will be negative. So here you can see in this row under 2 we write positive and under 0 we write negative, and node 1 is not involved, so put it as 0. Similarly, coming to row number 3 with respect to element 3, element 3 as you can see here starts from 0 goes towards 1. So under 0 you have to write positive and for 1 you have to write negative. So in third row under 0 I am writing positive, under 1 I am writing negative. Source is positive, source node is positive, destination node is negative, and the other node is not involved, put it as 0. So this is how we write A cap matrix. So from A cap matrix, we'll have to write down bus incidence matrix. So in order to write bus incidence matrix, we just have to eliminate the reference node. So in this particular case, bus 0 is the reference. So eliminating bus 0, we are left out with this matrix. We are just going to eliminate this particular column in order to get the remaining matrix, which is called as bus incidence matrix. Notation is A. The earlier matrix, element node incidence matrix, notation is A cap. Here the notation is capital A. So this is how we write bus incidence matrix. Further, after writing this bus incidence matrix A, let us apply Kirchhoff's current law at all the non-reference nodes. Reference node is 0, so we have to apply KCL only at 1 and 2. As per KCL, you know that total current entering a node must be equal to total current leaving the node. So if you apply it at node 1, I3 is current entering, I1 is current leaving. So you can write I1 is equal to I3. If you write it in the form of an equation, you have I1 minus I3 equal to 0. Then apply KCL at node 2. Total current entering this node 2 is I1. Total current leaving the node 2 is I2. So I1 is equal to I2. Write it in the equation form. I1 minus I2 is equal to 0. Call this set as equation number 1. Now after applying KCL at node 1 and node 2, whatever equations we are getting, call it as equation number, set of equations as 1. Then let us write this branch currents in matrix form. So we have three currents here, I1, I2, I3. They are the branch currents or the element currents. So if you write it in matrix form, it is a column matrix I1, I2, I3 called as I. Then we try to take transpose of A matrix that we have got in the previous page. We have got A matrix. So we try to take the transpose of A matrix. We have 1 0 minus 1 minus 1 1 0. Then let us try to multiply A transpose and I. So A transpose multiplied by I is nothing but 1 0 minus 1 minus 1 1 0 I1 I2 I3. So you know that this is a 2 cross 3 matrix. This is 3 cross 1 matrix. So resultant should be 2 cross 1 when you multiply them. So if you multiply them, first row into first column, I1 minus I3 will be the first element. Then second row, this column minus I1 plus I2. I1 minus I3 is the first element. Second element is minus I1 plus I2. But already from equation 1, if you see, I1 minus I3 is 0. I1 minus I2 is also 0. So I1 minus I3 is replaced by 0. And minus I1 plus I2 is same as I2 minus I1. Or I1 minus I2 is 0. Write it as 0. So from this we can understand that product of A transpose into I will give us 0. Let us call it as equation number 2. A transpose into I will always give us 0 for any given power system network. Next, for the same power system network, let us try to relate branch voltages and bus voltages. See, we are having three buses here, bus 1, bus 2 and bus 0. The bus voltage at bus 1 is capital E1, voltage at bus 2 is capital E2, voltage at bus 0 is E0. Then branch voltages are nothing but V1, V2 and V3. Now we just have to relate branch voltages with bus voltages. So coming to bus number 1 and bus number 2, in between the branch is 1, so the transmission branch is 1. So we write V1 is nothing but equal to E1 minus E2. V1 is equal to E1 minus E2 because the current flow direction is assumed to be flowing from 1 to 2. We take V1 is equal to E1 minus E2. Similarly, we try to write V2, which is E2 minus E0. E2 minus E0, since bus 0 happens to be reference, you can take the voltage as 0, you can write it as E2. Then V3 is equal to E0 minus E1. V3 is E0 minus E1. Bus 0 being reference, it is 0. So we will be left out with minus E1. So this set, let us call it as equation 3. Set of 3 equations will be called as equation number 3. Then Let us write down bus voltage in matrix form. Bus voltages are E1, E2 and E0 I told you. We'll write it in matrix form. We have E1, E2 and E0. Now let us try to multiply A matrix with Ybus matrix. Already we had got A matrix here. 1 minus 1 0, 1 minus 1 0, as you can see here. This will be multiplied with E matrix. And here product will be taken leaving the reference bus. Reference bus will not be taken into account. So you just have E1 and E2. This is our A matrix. Multiply the same. 3 cross 2 into 2 cross 1, you will be getting 3 cross 1. So A into E bus will get it as E1 minus E2 if you multiply them. And then second case, you get only E2. Third one, you'll be getting minus E1. Now if you compare this with our equation number 3, we know that V1 is E1 minus E2, V2 is equal to E2, V3 is equal to minus E1. So the same thing we are getting here. This is nothing but our V-bus matrix, V1, V2 and V3. So from this we can write it as V1, V2, V3 is equal to A into E-bus. So V in general V1, V2, V3 matrix can be written as V vector. So V is equal to A into E-bus. So this is our equation number 4. V is equal to A into E-bus. So in the earlier page, we had got A transpose I is equal to 0. That is one realization. The other realization is V is equal to A into E-bus. This is our equation number 4. So next further, we use our performance equation of the primitive network in admittance form that we have seen in the previous derivation. That is performance equation of our primitive element in admittance form is I plus J is equal to Y primitive into V. This equation 4, this is what we'll be seeing. So if we use that here, I plus J is equal to Y primitive into V. Pre-multiply the entire equation on both the sides by A transpose. Since we are involving matrix multiplications here, it is very significant whether you are going to pre-multiply or post-multiply. If you say pre-multiply, everywhere A transpose should be taken at the leftmost side. A transpose I, A transpose J, A transpose Y primitive into V. Because in matrix multiplication, we know that AB is not equal to BA. That's the reason why we have to mention pre-multiply specifically. And then one of the realizations. So, okay, after multiplication, you have A transpose into I plus A transpose into J is equal to A transpose Y primitive into V. So, from equation number 2, we know that A transpose I is equal to 0. And from equation 4, we know that V is equal to A into E bus. So we'll be using the same here. A transpose I becomes 0. So you will be left out with A transpose J is equal to A transpose Y primitive into V. So in place of V, I'll be writing A into E bus that we had seen here. V is equal to A into E bus, equation 4. So our equation now becomes A transpose J is equal to A transpose into Y primitive into A into E bus. This A transpose J it gives us algebraic sum of all source currents incident at each bus, because J represents source current vector and A transpose always represents a matrix relating the incidences of elements towards the nodes. So if you take a product of them, you will be getting total current injected at a particular bus, and this can be called as capital I bus because it gives you total current injected at a bus. So this can be rewritten as I bus is equal to A transpose Y primitive A into E bus. Let us call it as equation number 5. Now, if we generally relate by Ohm's law, we know that I is equal to V divided by Z, or you can write it as I is equal to V into Y. In place of impedance, if you take the admittance, 1 by Z is nothing but Y. So if you use that, you have I bus is equal to Y bus into E bus. For any bus, if you write the expression, I bus is equal to Y bus into E bus. This is our standard expression. So compare 5 and 6. Compare equations 5 and 6. If you compare them, you have Ybus is equal to A transpose Y primitive into A. So Ybus is equal to A transpose Y primitive into A. This is the expression for Ybus by singular transformation, where A is our bus incidence matrix, YPRI represents primitive admittance matrix, and this represents admittance matrix. So do not get confused with the capital Y and small y. Whenever you write small y, it is referring to primitive matrix. When we write capital Y, it is referring to admittance matrix. Y bus is different from Y primitive. So let us be careful while writing Y. If we write small y, it refers to primitive matrix. Capital Y refers to admittance matrix. So this finishes the derivation of Y bus by singular transformation. And examination point of view, again, Y bus by singular transformation is there in every question paper. So for this derivation, you can take any sample network. What we'll have to do here is first draw that particular network, write down the graph for that, and try to find A matrix. This finishes the first part of the job. We can split this into 4 parts. In the first part, take any random power system network and obtain A matrix. This is the first part of the derivation. Second part of the derivation, you have to realize A transpose into I is equal to 0. This is the second part of the realization, where we apply KCL at various nodes, especially non-reference nodes, and then take the product of A transpose into I for the same network and get the expression A transpose I is equal to 0. This is the second part of the derivation. Third part of the derivation is try to relate branch voltage and bus voltage, write the expressions, take a product of A into Ybus and arrive at the expression V is equal to A into Ybus. This is the third part of the derivation. And fourth part of the derivation is use our primitive equation of performance equation of primitive network in admittance form, I plus j is equal to y into v, and then simplify it based on the results we have got in the previous stages, and try to get y bus is equal to A transpose y primitive into A. So there is no compromise with this derivation. This is a definite question in each and every examination. So this completes the derivation of Y bus by singular transformation. Next, let us take up a problem on Y bus by singular transformation. So obtain Y bus by the method of singular transformation for the given network having the following data. So generally, whenever they give a problem on Y bus by singular transformation, not necessarily they'll be giving you the graph or the network. They may give it in the form of a table. From the table, you will have to draw the graph, or in some problems, network will be straight away given. So in this particular problem, they have furnished the data in the form of a table. So let us see what the table is. First column is element number 1, 2, 3, 4, 5. Second column is bus code between any two buses P and Q. In general, PQ. So 0 to 1, 1 to 2, 2 to 3, 3 to 0, and 2 to 0. And here they have mentioned self-admittance in per unit 1.4, 1.6, 2.4, 2, and 1.8. Remember, only the real part is given over here with respect to admittance. You know that admittance y is equal to g plus jb. B is not given, only g is given here. In case they mention the coefficient j, then the susceptance would have been given. So try to remember y is equal to g plus jb. Only g, the real part of admittance matrix, is given in the problem. Now here, this from the data itself, we can understand that this is a 5 element. There are 5 elements in this network, and there are 4 buses: bus 0, 1, 2, and 3. 4 bus power system network. So for this 4 bus power system network, we'll have to get Y bus by singular transformation. Self admittance data is given here. Now the formula is Y bus is equal to A transpose into Y primitive into A. We have to find this A, we have to find Y primitive, do the matrix multiplication to get Y bus. So from this given data, let us draw the oriented graph so that it will be easier for us to write A matrix. So here, first we have element number 1. see in this given problem there are four buses, so randomly mention four nodes here. Since I'm writing oriented graph directly, I'm mentioning node 0, node 1, node 2, node 3 randomly. I'm going to place them and then interconnect them using lines. First line is line number 1 or element number 1, which is between 0 and 1, and the direction of current is also from 0 to 1. So we have 0, we have 1 here, connect a line here between 0 and 1 and give the direction as 0 to 1 as given in the data and mark it as element number 1. Next we have element number 2, bus code 1. This element number 2 is present between bus 1 and bus 2 and direction is bus 1 to 2. So bus 1 to bus 2 direction is this one and then element number is also 2. And then element number 3 is between buses 2 and 3. So but between bus 2 and bus 3 draw a line and call it as 3, give the direction. And element number 4 between bus 3 and bus 0, direction is 3 to 0. So between 3 to 0 it is element number 4 and give the direction. Element number 5 between bus 2 and 0. So draw a line between bus 2 and 0, call it as 5 and give the corresponding direction. And 0 is to be taken as reference. So this is the way we write the we draw the oriented graph from the given data. Just consider how many buses are there, represent the buses or nodes, and then elements also we have to represent along with the directions as per the given data. From this data of oriented graph, we'll have to write A matrix. Either you can write A cap matrix and then write A matrix, or directly by now we should be in a position to write A matrix straight away. So A matrix we should not contain the reference node. So I will be mentioning elements over here vertically 1, 2, 3, 4, 5. I'll be representing the nodes here 1, 2 and 3, and node 0 will not be taken because directly I'm writing A matrix. If there is any confusion in writing A matrix directly, you can first write A cap and then remove the reference node to get A. So here, as usual, consider the first element. It is from 0 to 1. So for 0, we should write +1. 0 is not there. Directly for minus under 1, we write -1. 2 and 3 are zeros. Coming to element number 2. Element number 2 is going from 1 to 2. 1 is positive, 2 is negative. Element number 2 in row 2. 1 is positive, 2 is negative. Remaining are zeros. Coming to row number 3. In row number 3, element number 3 starting from 2 going towards 3. So it will start at 2 means under 2 we write positive. Destination node is negative. Sorry, destination node is 3, so it is negative -1. Other elements are zeros. Then we go to row number 4. Element number 4 starts at 3, goes towards 0. So 3 will be positive, under 0 it will be negative. 3 will be positive, 0 is not there, we are not going to write. The remaining elements are zeros. Element number 5 starts at 2, goes towards 0. So 2 under 2 it is positive, 0 it will be negative, 0 is not there because we are writing A directly. Other elements are zeros. So this finishes our A matrix. So for our formula, we need A transpose. Take the transpose of the A matrix to get this A transpose. Next, we need Y primitive. So we know that generally to write primitive matrices, first we write down Z primitive, take the inverse of that to get Y primitive. And when we are writing Z primitive matrix, diagonal entries will be self-impedances, off-diagonal entries will be mutual impedances. So that being the case, here in this particular problem, they have given admittance data straight away. They have not given any impedance data. They have given admittance data. Since they have given admittance data directly, instead of writing Z primitive, straight away we can write Y primitive. Moreover, mutual impedance is not present here. If mutual impedance data or admittance data would be present, we have to write Z primitive, then only find the inverse of Z primitive. But here only admittance is given, self admittance alone is given. So it's straightforward. We can just drop the element, self admittance elements here diagonally. From this, we know that there are 5 elements. So the size of your primitive matrix will be 5 cross 5. Only self admittance data is given. So diagonally, just mention them. So for element 1, 1.4, element 2, 1.6, element 3, 2.4, element 4, 2, and element number 5, 1.8. That will be Y11, Y22, Y33, Y44, Y55. So Y11, Y22, Y33, Y44, Y55. No mutual coupling elements are present, so all other matrix elements will be zeros. So this is how we get Y primitive matrix. Then at last we are left out with the formula Ybus is equal to A transpose Y primitive into A. So we write A transpose matrix here in between Y primitive and A matrix over here. So perform the matrix multiplication to get the final result. Ybus is equal to 3 minus 1.60 minus 1.6 5.8 minus 2.4 0 minus 2.4 and 4.4. So this is how we find Ybus by singular transformation. In the examination, sometimes we'll be facing problems where a network will be given and they'll ask to find Ybus by inspection and verify the same using singular transformation method. So both the methods must be known to us.